Great. Well, thank you. Yeah, so I just want to talk to you about some work that I've been doing with Graham Hutton and Patrick Barr. And really, the story begins with compiler calculation, which I think is sort of a very powerful form of magic. And the problems that we encounter when we look at this alongside side effects in our languages. So just for a bit of background, there are sort of two ways that we can write a compiler. But the things we want are the same, right? So we have a language, and we want a compiler for this language. And we also want a virtual machine that can take the code generated by this compiler and run it. And in an ideal world, we also want a proof that these two things are correct, right? That they actually do what we want them to do, because without that, it's not very much use, I suppose. So the traditional way is we might define our instruction set. So this is going to be things like push, pop, add, halt, that kind of thing. We'd take these instructions and we'd write a compiler that takes our code, generates these instructions, and at the same time we might write a virtual machine that takes the code generated by the compiler and then actually runs it. And then again, in an ideal world, we would prove that these things do what we want them to do. The thing is that actually writing a compiler is a bit of a pain. Anyone who's written a compiler before probably will know this firsthand, that it can be a bit of a tricky thing to actually write one. And proving that it's correct is even more of a pain. I've never proved by hand a compiler before, but it doesn't seem like a very fun thing to do. But the nice thing is that we can actually take a different approach here, and we can sort of flip this problem on its head. So we can start by trying to prove the correctness of our compiler. And the thing is that at this point, the compiler doesn't exist. So we get a little bit stuck, but then we realize that we can sort of define the compiler so that it is correct by construction. The compiler, the virtual machine, and the instruction set sort of fall for free out of this proof, which is I guess why I'm saying that it's some form of magic, right? It's summoning magic, maybe. So yeah, but it works, right? There are a lot of papers about this kind of thing, especially in recent times, is sort of coming into its own. Not all of these papers are directly related, but they're all somewhat related and all very interesting ones I would recommend. But the thing is that there has not been very much work on languages with side effects. And in fact, the work that has, in terms of compiler calculation, of course, there's been lots of work on side effects, but, and the work that has been done has not really focused on actual side effects. It's more been sort of simulating them in some sense, which is what we're dealing with here. We're dealing with how can we actually apply these techniques to these languages, right? But yeah, just a bit of background. So compiler calculation in a pure language. I'm going to start off setting this up, and then I'm going to move over to augmenting this with the side effects. So here's our language that they're going to be working with. We have values, we have integers, and we also have addition of these integers. So it's a very simple language, hence the razor. But here's an example expression here, right? So we're adding 1, 2, and 3. And we can define our semantics for this language. It takes an expression, and it gives us an integer. And I'm sure you've all seen this before. We evaluate an addition by evaluating the two sides separately and then adding together those results. And I've got a nice little animation of exactly how this particular expression would evaluate to 6, hopefully. And the question now is sort of what does it mean to compile this language? So I think we probably all have an intuitive idea of what a compiler is, but if we want to use this intuition to actually calculate a compiler and a virtual machine, we sort of need to formalize this intuition a bit. So this is going to be specifying the compiler. And I mean, the first part of this intuition is really that a compiler is a function which takes an expression and it gives us some code. And I suppose this is probably an obvious thing if you really think about what is a compiler. But the less obvious thing is what exactly this code is, because at this point, we don't know, right? We want to calculate this. So I'm just going to leave this code undefined for now. But I can do it in a little diagram, so we have the expression coming in from the side and give some code back. Okay, and the second component really is the virtual machine itself. So This virtual machine is a function called exec. And hopefully this is intuitive as well, that a virtual machine takes some code. So this is like a list of instructions. And it turns this into a stack transformer because, well, we want to target a stack machine. So that's the sort of natural thing to do here. And again, I can show this in the diagram. So we can take our code that we've generated, plug this into the virtual machine with an empty stack, and then it's just going to put the result on the top of the stack. Okay, and you can actually look at these two components here as sort of factoring the eval function. So on one hand, you could compile and then execute the result of that, or you could just evaluate directly. And either way, you're going to get the same thing, hopefully. So there's a bit of like unwrapping of putting the result of the eval onto the stack, but you can kind of ignore that for the time being. And we can write this in an equation. So we can say exactly what I just said. On the left hand, you can compile your expression executed on a stack S. And on the right-hand side, you could evaluate your expression and put it on the stack S, and you should get the exact same result. One quick note is that in practice, when we're actually calculating these things, it becomes a lot more practical to give a continuation in the compiler as well. So this is just like an extra bit of code to bolt onto the end. But this is purely just, it makes the calculations a lot nicer and a bit more efficient code and that sort of thing. So don't worry too much about that. The next thing we do at this point, so we've done our specification, right? We've got this equation, and we actually want to now calculate the compiler, right? So we have this equation. It has three unknowns, and really just like in maths, right? We can solve an equation. It's a little bit strange that it has more unknowns than equations, but we can get onto that later. But yeah, we can solve this, right? And we'll get a compiler, we'll get a virtual machine, and we'll get an instruction set for free. We solve this by something called constructive induction. And again, I'll get onto this later, but what I'm going to do first is augment this specification with side effects. Because the thing is that real programs do have side effects in almost all cases, right? We want to output things, we want to take user input, we want maybe some mutable state, some references, some these kinds of things, right? So that's the rest of the talk, really. I want to talk about how these side effects sort of alter the specification that we need to do for this calculation, how they alter the actual calculation itself, and what we get out of the other end, and sort of how we can deal with them just in general, really. So I'm going to investigate this just with something simple, printing. Printing is probably the most simple effect we could get, other than kind of like the no-op effect, which would be a little bit boring. So yeah, let's come back to this minimal language we have. And I want to give it printing, right? I want to give us the capability to print something. So yeah, very simply, I'm just going to add this print constructor. And the idea is that evaluating a term of print x, we want to evaluate x and then actually print the result of that, right? But the thing is that since our semantics are just giving us an integer, we can't actually print anything. So, as Haskell programmers, probably the obvious thing to do at this point is to change this up to work in the IO monad, because then we can just use the print function, right? We can print it to the screen. The problem with this is sort of needlessly specific. This gives us a lot of power we don't need. We don't need to have the ability to, get line or open files. All these sorts of things, right, are kind of just getting in the way. And further along the line, we'd like to generalize, and it kind of gets in the way of that. So what we want is the minimal possible structure to represent sort of this transformation of an expression with some prints into a sequence of things that have been printed. Ideally with nothing more, because we can then take this and interpret it however we like. So yeah, we prefer this abstract algebraic approach to effects, and I'll talk about a little bit more the algebraic side later on. But for now, here is a type that we could use for this, right? So I'm going to call it print sequences. And the idea is that we can either return something, and this is just like the thing at the end of the sequence, or we can print an integer and then continue with the rest of the sequence. And just a little example that this 1, 2, 3 thing would just be exactly that. And we can take this and we can throw this into our semantics function here, just replacing IO. Obviously, we can't use print anymore, but we can sort of define an analog to print, which is called printint. And very simply, it describes this action. It doesn't actually print, but it describes the action of printing an integer and returning nothing. So very much the same as Haskell's print function. So that's good enough for the semantics, but now we need to come to specifying the compiler itself. The first thing is that we've now changed the type of eval, so let's reflect that there. Of course, the equation doesn't hold anymore, from a type perspective even, because eval's changed. So, if I draw that on the diagram, we can see that eval before it just gave us this 3, but it now gives us the printing a 3 coming out of the bottom. And we need exec to line up. So all we need to do really is have the exec function also work in this print sequence monad. We can also change the equation at the bottom to reflect this. So the right-hand side is now is under a do block. So we first get the result of evaluating something, and then we push that value onto the stack and execute the rest of the code. But the left-hand side remains the same. So that completes the setup, really. Now I'm going to move on to actually calculating this thing, right? So as I said, it's just like in maths in many ways. We use induction, and when we get stuck, we can sort of take this opportunity to add new constructors or add new defining clauses for our equations. This is going to be by cases on the type of expression we have. So first I'll show you the calculation for the value case, which is sort of our base case. And here's the strategy. Okay, so we're going to start on the right-hand side of the equation at the bottom, substituting value in. And what we really want to do is get to this point. So we want to rearrange this expression into something of the form exec c prime for some c prime, which we don't necessarily know what this is yet, but this can actually be anything we want in this stack S. Because if we can do this, then if you look at the equation at the bottom, we could actually say that a valid definition for comp at this val type, this val expression, is just c prime, because if you substitute that in, it checks out. And if we could do this for all of our expression cases, then we'll have a fully functioning compiler. So let's try and do that. First thing is I'm going to just apply the definition of eval, which gives me this. I'm going to use some monad laws to sort of shift things around, clean it up a little bit. But now we're sort of stuck because we want these two things to be equal, but the stacks are different, right? We have encode on S on one side, and we have S on the other side. But remember that c prime here is sort of a free variable. We can change this to be anything we want. We can also introduce new instructions because the code type is undefined as of yet. So what I'm going to do is actually define a new instruction, which I'm going to sort of suggestively call push. And I'm going to put all of my free variables in here, so n and c. And then I'm just going to define the exec clause for this specifically so that these two things are equal. And then, then the nice thing is that now I have this in exactly the form I wanted, right? So my c prime is now this push nc. And as I promised, this means that I can define this clause for the compiler function, that compiling a value is just going to translate to this push instruction, right? And with that, we've calculated a few things already. We've calculated this one instruction of code. It's not complete yet, but we've got one instruction of it. We've calculated one defining equation for the exec function, the virtual machine. And we've also calculated one defining equation for the compiler. So really, you can imagine if we did the same for add and print, we would get a full definition of each of these things. And that's exactly what we'll do now. So the add case is a little bit more involved because we have to use induction. But that's quite nice because it sort of gives us something to move towards in the calculation, right? So I'll start in exactly the same way. And again, I want to get this into something of the form exec c prime s. So again, I can use my eval definition, which we've been given, and I could also use my monad laws, which gives me something of this form. But now really I want to apply induction, and induction is going to be using this specification at the bottom and rewriting according to that with a smaller argument, obviously. And so you can see, like, it's almost of this form at the bottom right. You see I've squared this bit here where in the expression that I actually have, at least at the end of it, I have an m comes from eval y, and then I have an xxc with something to do with that m on top of the same stack, s. But it's not quite, because I have the n plus m rather than the m. But I can just use the same trick. So, this is what we want. And I can just add a new instruction to put it into this form, right? So I can add an instruction called add, which rearranges things exactly in the way that I need to put it into this form. And if I do that, I can then now apply induction once. Fortunately, it's in the form again where I can apply induction a second time. And that leaves me with this. And remember that we wanted something of the form exec of c prime for some c prime, any c prime, in this stack S, and that's exactly what I have. So yeah, just like before, I can now take this opportunity to define a new defining equation for the comp function, right? And finally, just actually very similar to the add case, I'm going to do the print case. Again, we want to use induction, but this time it's only once. And the tricky thing here is that we have this print int in the way, and this time it's the print int that is actually blocking us from applying induction. So yeah, unsurprisingly, I'm going to take the exact same trick again, and I'm just going to make this new instruction, which sort of just gets it out of the way pretty much. It sort of hides, not hides, but you could say it hides the fact that we're actually printing this thing under the instruction itself, because the instruction can be anything we want. And then again, we're now in this position where we can apply induction. We apply induction, and we get the form we wanted at the end. And I can now, I can use this to define my new clause for the comp function, right? And just like magic, I now have a fully functioning compiler, a fully functioning virtual machine, and a set of instructions, right, forming my code. And I tell you it's fully functioning because, by construction, these things must satisfy the specification that I've given, which is pretty cool, I think. There is one thing that I'll point out. The eagle-eyed among you may have noticed that this code type actually has no finite terms, because we're always going to be having to push some code onto the end. The fix here is that we actually just add a halt instruction. And then executing halt with some stack just returns that stack directly, because there's nothing left to do. And actually, this can be calculated as well. We can specify this compile function at the top, which just called halt at the end of the compiler. We can specify that in an equation, solve the equation, and we get the halt again for free. But the details for that are not super important for the time being. But that's the compiler. Now, the thing is that the virtual machine doesn't actually print anything. So, is this really a side effect? Because we're just building up this sequence of prints, right? But these are not actually being printed. These could mean anything. It's a good question. But actually, the nice thing about this is that this really means we can interpret this print effect however we like. We could do the obvious thing, right? Which would be to sort of just take this print sequence and turn it into an actual I/O action which performs these prints. So, in the case that we have a return at the end of our print sequence, we just map this to a return in the I/O action itself. And in the case that we have a print int, so printing n followed by the print sequence p's, we would just actually print. So using the actual I/O action print, we'd print this integer, and then we would continue to run the rest of the print sequence. But we can do some more kind of crazy things. Well, not super crazy yet, but we could just collect up the list of things to be printed without actually printing them. very simply just putting them into a list here using the cons operator, really. It's nothing more to it. Or we could actually, like we could reverse the order of printing. So this one's kind of cool, I think. We interpret printing n followed by a print sequence p's by first running this remaining print sequence p's in reverse order, recursively, and then only once that's done, we actually print this first thing that we started with, and then we return the same value at the end. And then you could imagine, right, like, this could then feed into one of the other interpretations. It's quite a flexible way of looking at things, I think. And this just comes from the abstract kind of like algebraic approach to this. We wouldn't be able to do this if we used I/O actions to encode these things. And so, yeah, I mean, in summary, what we've done really is that we've calculated a compiler, we've calculated an instruction set, and we've calculated a virtual machine for a language with output, so with a print effect. And we've got these things for free, so we know that by definition they're correct. There's no need to write a proof post hoc because it's guaranteed correct by construction. We've taken this algebraic abstract approach to effects, which has let us interpret the outputs of these things in any way we want. And actually, there are a lot more examples of the interpretations in the paper. There are some quite interesting ones, especially for the other effects. So these allow for all these different interpretations. And then also, in the paper, we've considered a few different other effects. So we've considered mutable state, so with get and set. Actually, this one's a little bit more interesting because get and set have slightly different definitions rather than just doing something. We're actually getting some data and then proceeding differently based on what we have. So you get some continuations in there, and it's quite a nice example, I think. And then also non-determinism. So a bit weird to think of non-determinism as a side effect, perhaps, if you've not seen that before. But we've calculated compilers and virtual machines for both of these things as well. And also there are lots more interpretations of all of these effects in the papers that you might want to take a look at. We've also generalized all of these things, so using type classes. So you might have noticed that in the calculations, we didn't actually use the print sequence monad, the definitions of how it was defined, how the print int function is defined. This doesn't come into the calculations at all. So what we observed is that we can kind of extract this out even further and find a type class for any monad that we can calculate, for instance, a print effect using. And then we've calculated it in general using this type class. And we've also looked at generalizations using free monads because, I noticed that the print sequence type is, in fact, a free monad, and as it happens, all of the effect kind of algebraic effect types that we consider are free monads of some signature. So we looked at that as well in the paper. If you're one of the people who care about these types of things, we formalized all of these calculations in Agda, so don't worry about them not being correct. Although I don't know, Agda's not the best language for this, in my opinion, but it's all there if you're interested. There's some further work that we'd like to look at. So, primarily I'd like to look at some more sophisticated source languages, so, and in particular first-class handlers, right? So it would be really great if you're familiar with algebraic effects as sort of a concept, then you have this idea of you can write a handler and wrap your code in this, and that lets you sort of, you can intervene when an effect comes up and you can do something. This is very similar to the interpretations that we're doing after the fact, but it'd be great if the users of the programming language had this power as well. So it'd be good to calculate that language also. And then also just sort of more sophisticated things in terms of maybe lambda calculus, or maybe we have variables in here, or that sort of thing. Then it would also be good to calculate sort of one compiler in general for any effect, because having done the calculations for printing and having done the calculations for getting, setting, choice in non-determinism, it turns out that the calculations are very, very similar to each other. And this is something that I've started working on now, which is, can we actually calculate a compiler once and for all, and then just plug in an effect we want in a very general way. And it turns out that yes, we can. And I can talk to you about the details if you like later on. But it's quite a cool thing to look at that. And then finally, I think there's some additional structure just in like the semantics and in the sort of the setup in general that we can probably exploit during these calculations. So, I mean, for instance, yeah, I mean, the eval function is a fold, but we're not writing it as a fold, but it is a fold. Presumably, that can simplify the calculation somewhat, right? And then also, you know, looking at these free monads and these things, I think that the calculations, while nice, could definitely be simplified a lot by considering some of this additional structure that we have. So that's all I have for you for now. Thank you for listening.
Yeah, we have time for questions.
Hi, Pedro Vasconcelos from the University of Porto. So, can you go back to your first slide, which has the non-effectful specification for the compiler? Yeah, the first sort of one we have exec, eval, and run, and what's the specification for the compiler? Yeah, after that.
This one takes a second, sorry. So this one, you mean?
Yes. So the thing is, in this case, there are actually many solutions to how you'd get that.
Yes.
And one, I'm now sort of playing the devil's advocate, inspired by the keynote by Andrew Gordon, playing the AI who was given this specification. And my specification could be code equals exp, stack equals, does void, and eval, and compile, and exec equals eval. So
I'm very, very glad you said that. Yeah, so it's a really interesting question.
Where's the trick? Where did your, you input the fact that you really wanted a compiler and not just the identity function?
So the answer in terms of the way that we're doing the calculations at the moment is really, you know, we sort of have these implicit constraints in our mind of, okay, well, I don't want the compiler to make use of the eval function, and I don't want, you know, I don't, and it sort of, the thing is, doing calculations in this way, it really exposes the decision points, right? So rather than, it kind of gives you these choices to make. But one thing that I am really interested in, and which I can give you a good answer on in a moment if you want, but there's not enough time now, is that actually we can really pin down precisely what we want by using things like, you know, if you say that, for instance, the compiler has to be a natural transformation, right? That gets rid of looking at the values themselves. So you can have properties like this, which would force more structure. Yeah.
Thanks.
Thanks.
Hi, Sam Lindley, University of Edinburgh. Very nice talk. Thanks.
Thank you.
I was wondering, can you handle higher order or scoped effects? Do you know what I mean by that?
Yeah, I see no reason why not, but it's not something that we've considered.
So, I mean, I'm thinking an example, you might have a fork operation that itself takes a computation as an argument. So if you were to do folds, for instance, then you need a more sophisticated kind of fold in order to traverse over that term, because you have to go inside the argument as well. But
yeah, that might, well, that probably would negate any benefit we'd get from looking at folds in these things. But yeah, other than that, I don't see.
Well, I don't think it would if you need to look at the literature on that, and that would tell you how to do it. But scoped effects. But
yeah.
Okay, but you've not looked at it yet.
We haven't done it yet, but actually that's a nice idea. Yeah.
And yeah, I'm very keen to see what happens when you try to do handlers.
Yes, likewise. Likewise.
Right, thanks.
Thank you.
Hi, John Hughes, Chalmers and Cubic. So when I see people give this kind of talk, it looks like a question of kind of turning the handle and the compiler just drops out beautifully. And I wonder, how much is that handle turning automizable? Is it conceivable that one might write a tactic for some theorem prover that does this, you know, and does everything by itself?
Yeah, so a really interesting question. Oh, well, I just pressed. Oh, I pressed something. Yeah, because one thing that, in fact, it kind of goes back to this question before of, you know, why don't we just get trivial solutions? And if you look at the answer to this, then what you can do is, while you're going through, a lot of it is mechanical. So you're applying eval, you're applying monadors. A lot of it's mechanical. And then you get to these decision points. So this was the thing, I won't even try and find the slide, but it was the decision points like, oh, okay, I'm going to introduce an instruction here. And this is when it gets stuck. And what you can actually do is you can take this out as a constraint. And if you collect together all of these constraints, then you can kind of skip past them and deal with them at the end as you like. So I think that, yeah, it's very possible to write a system that mechanizes everything except from these decision points, and then allows the programmer to deal with them at the end. Yeah, I think that'd be a really interesting thing to do.
My other question was, this is a way of calculating a one-pass compiler where you invent the target language, but many real compilers have more than one pass.
Yes.
Is the same idea applicable to developing later passes, or is this idea really targeted at the first pass?
Well, do you mean in terms of things like optimizations, or in terms of like typing?
Yeah, for example, could you imagine constructing a compiler with several passes by calculating each pass separately?
Yeah, I could definitely imagine that. And in fact, something that I've been thinking about just recently is calculating type systems. So kind of, specifying some property you want, and then some, you can kind of, I think you can do these things where, depending on how you set things up, you can get like different properties of your intermediate languages, and you can kind of, I wish I had a better way of putting this into words, but yeah, I think it's very, very, very possible. I do, yeah.
Should we do one more quick question while the next speaker gets set up?
I want a register machine and not a stack machine.
Well, Graham and Patrick have some papers about this, but
Okay.
We've not looked at it for effects yet, but it's definitely a very, very possible thing to do, yeah. A paper called Calculating Compilers 2, Return of the Register Machine, I believe, might be worth taking a look at.
Okay. Let's thank Zach one more time. Next speaker is going to be Craig Ramsey. He's going to tell us about his concurrent hardware garbage collector.
Am I?
Copy my slides. Do you want to swap laptops?
I can see it on the screen down here, so I'm not sure what's going on.
Are those your slides?
Yeah. Sure.